If a powerful quantum computer became operational tomorrow, much of today's internet security could become vulnerable overnight. Bank logins, secure websites, encrypted emails, even blockchain systems. The threat isn't science fiction, it's mathematics, and the solution is something called post-quantum cryptography. Why today's encryption works set the foundation. Right now, the internet relies on public key cryptography. Algorithms like RSA and ECC protect secure websites, VPN connections, digital signatures, software updates. These systems are secure because classical computers struggle with certain mathematical problems, for example, factoring extremely large numbers or solving discrete logarithms. For normal computers, these problems would take millions of years to solve. That's why your browser shows a lock icon. But that security assumption depends on one thing: computers staying classical. What changes with quantum computing? Quantum computers don't use traditional bits, they use qubits, and qubits can exist in multiple states at once, a property called superposition. In 1994, mathematician Peter Shor introduced an algorithm showing that a sufficiently powerful quantum computer could factor large numbers efficiently. That means RSA could be broken, ECC could be broken, not slowly, but dramatically faster than classical systems. We don't yet have large-scale, stable quantum computers capable of doing this, but development is accelerating. And here's the real concern. Harvest now, decrypt later. Even if quantum computers aren't ready today, attackers can already start collecting encrypted data. They store it and wait. This strategy is called harvest now, decrypt later. Sensitive data like government communications, medical records, financial transactions, intellectual property. Some of this data needs to remain confidential for decades. If it's stolen today and decrypted 10 years later, the damage is still real. That's why quantum risk is not just future tense, it's present planning. The solution: post-quantum cryptography. Post-quantum cryptography, or PQC, is the effort to build encryption algorithms that even quantum computers cannot efficiently break. Unlike quantum communication systems, PQC runs on classical computers. It simply uses different mathematical foundations. These include lattice-based cryptography, hash-based signatures, code-based systems. The idea is simple: replace vulnerable algorithms before quantum capability becomes practical. Governments and standards organizations are already evaluating and standardizing quantum-resistant algorithms. Enterprises are testing hybrid models, combining classical encryption with post-quantum algorithms during the transition. But this shift is complex. Updating global cryptographic infrastructure takes years, maybe decades. Why this matters? The internet won't collapse overnight, but the transition window matters because encryption protects not just money, but identity, privacy, national security, intellectual property. Quantum computing doesn't automatically break the internet, but it forces us to rethink the foundations of digital trust. The real question isn't whether quantum computers will advance, it's whether our encryption advances faster. In cybersecurity, the safest strategy isn't to wait for disruption, it's to prepare before it arrives.